Be right back.
Okay, so I guess we can start. So welcome to that first MECAQ seminar. So we hope to be able to offer something like a monthly online seminar. And our first speaker today is Jack Harris from Yale University. So sorry, not Yale, Jack did his, I think, undergraduate degree from Cornell University. Then he went to do his PhD in Santa Barbara in condensed matter physics. Then worked as a postdoc at Harvard with John Doyle, and eventually was hired at Yale University, where he started working on optomechanics around 2005. Well, Jack is very well known for introducing very novel optomechanical systems. The first and the very famous one is mechanical membrane in the middle, which has been a very important system in optomechanics for 15 years now, or so. And also recently introduced working in optomechanics with just superfluid helium inside optical fiber cavities. So Jack, it's a pleasure to have you, and so you're very welcome to start.
Yeah, thank you. Can you hear me okay?
Yeah, sure.
Okay, so again, let me thank Pierre-Francois for the invitation to give this talk. It's a real honor to be giving the first talk in this series. I can't see you, any of you, but I'm assuming that there are some people here, and of course, it's a pleasure to be speaking in front of the optomechanics community in France. I'm sorry not to be there in person, but I'm grateful for the chance to be connected in this way. So today I'm going to be talking about measurements of phonon statistics in a superfluid optomechanical system. Before I get into the details of the experiment, though, I'll start with some background. First, some background really just on optomechanics, and maybe for this community, this is not necessary, but I think, anyway, I'll just give you sort of my take on what I see as some of the motivations for this field. And in particular, thinking of this field as a way to access quantum phenomena on unprecedentedly macroscopic scales. With that as a goal, I'll introduce superfluid helium as a material for doing this kind of physics. I'll talk about the use of single photon detectors as single phonon detectors, and basically talk about how we use the back action of photon counting measurements as a non-linearity in our system. Then we'll actually get to the meat of the results and talk about measurements of phonon statistics in superfluid helium, and I'll try to give you some sense of where I think these devices can go next. I should start out my talk by acknowledging this is a close collaboration with Jacob Reichel's group in Paris. I want to thank the students, Ichi, Lucy, and Sean, who've worked on this project, and especially highlight the postdoc, Yogesh Patil, who's really led this effort. And of course, our theory collaborators. Okay, so optomechanics, you may, this may be old news to you. You may have heard me say this before, but I'll just say it again. I think taking a step back from optomechanics itself, I think it's exciting to try to explore quantum mechanics on large size scales, however you want to define that. And I think there's some people for whom, like, you just say those words and they say, ah, yes, that's an obviously exciting thing. Some people might say, but why? We know quantum mechanics works. What's the point here? And I would say there's sort of three ways to motivate this. One is just pure curiosity. I mean, if this sounds exciting to you, I think it should. I find it inspiring that in Marcus Arndt's group in Vienna, they can take molecules that look like this and literally, just like in the Gedanken experiments, send them flying through a vacuum chamber for meters, have them pass through real physical slits, actual holes in a screen, just like Niels Bohr and Albert Einstein drew in their debates, and then collect those molecules on a phosphorescent screen where each flash is the arrival of a molecule, and see the interference pattern that's associated with the wave function of this big object's center of mass. This is just amazing. You can really do this, and it really happens, and it really works. And if all this field ever did was to keep doing this for bigger and bigger objects, I would regard this as a worthwhile endeavor. Very exciting. At the same time, though, there are real, very sophisticated technologies for physics detection, for cell phones, for signal processing, et cetera, that are built on exquisite mechanical devices, all of them almost operating in the classical regime. And it's a fair question to say, if you take a really mature technology and can add quantum resources to it, the chances are you're going to be able to improve the performance of these systems. We've already seen that in gravitational wave detection. Lastly, it's possible that the quantum mechanics of macroscopic objects is not just what you would extrapolate from the quantum mechanics of microscopic objects. You know, there's never been a theory of the physical universe that has proved to be correct over all size scales and length scales and over all domains. It's possible that there are terms in the equation of motion that go beyond the usual linear Schrodinger equation, for example, in the postulated models of objective wave function collapse and the like. We know that there are unanswered questions about how space-time is described in a quantum mechanical picture, and it has been hypothesized that we might get some experimental insights into that story by exploring what happens when you take a massive object and put it in a superposition, and then ask, given that there's a quantum superposition of mass density, what does the corresponding space-time geometry in the vicinity of this system look like? We don't have a theory for this at present, and at least some people think that we might be able to learn something about it by working with laboratory scale masses in quantum superposition. Anyway, so these are three kind of broad overviews for motivating the study of quantum mechanics on macroscopic scales. Optomechanical systems are one way to think of doing that. In an optomechanical system, from this point of view, the object of interest is some relatively massive object, which we imagine is confined harmonically. It's free to oscillate. And we'd like to know whether there's anything interestingly quantum mechanical about this object's center of mass, say. And a nice way of trying to answer that question is to start with a microscopic system whose quantum states we understand well, we can prepare well. In this case, that's the electromagnetic field, various modes of it. And we know from quantum mechanics that if you have a certain quantum state of one system and you introduce a unitary coupling between that system and any other system, in general, they evolve into some sort of entangled state. And if you are then able to measure one of those subsystems, in this case, again, a mode of the electromagnetic field, you can infer, you won't have direct access to the quantum dynamics of this object, but from what you can measure on one of the subsystems, you can learn something about what the other subsystem has been doing. And optomechanics implements this by, as I said, starting out with light, photons, as the microscopic quantum system, getting it to interact with the center of mass of some big physical tangible object via radiation pressure. Radiation pressure is famously weak, it's pathetically weak, but it is unitary, and it's a unitary coupling between these degrees of freedom that we're interested in. And then letting the light leak out of whatever cavity enables this radiation pressure effect, letting that light leak out and then be detected using any of our standard photo detection technologies. So this is the basic paradigm of optomechanics, and it's a faithful realization of the kind of stories that Bohr and Einstein were telling in their debates about quantum mechanics. There are some technical challenges involved, and one of them is just the weakness of this radiation pressure effect. 1 second. Okay. Let's see. Okay. Do you see a full screen again? Jean-Charles?
Yeah, it's okay, Jack.
You see the full screen and everything?
Yeah, sure.
Yeah, it's okay.
So the so the system is described by this Hamiltonian, which just represents the fact that this cavity is detuned by an amount proportional to the displacement of this object. And what maybe the central technical challenge here is just that the coupling, which parameterizes the strength of this radiation pressure effect, tends to be very small. And the relevant scale here is by how many hertz is this optical cavity detuned by this mechanical object's 0-point motion. Typical macroscopic object is a 0-point motion, femtometers. That's probably not a giant detuning of the cavity, but it's what we have to work with. Given the smallness of this effect, in general, we want things like high finesse cavities. We want strong coupling. We want sort of low mass objects here. We want the impact of the thermal environment to be as small as possible. We want this mechanical oscillator to have high Q, and we want the whatever bath it's coupled to be as cold as possible. But it turns out to also be crucial to have some type of nonlinearity present in the system. And I'll say more about why that is in my next slide, but for now, I just mentioned that as a point. In such devices, we care about various ratios that set dimensionless figures of merit, like the cavity finesse, the mean phonon number in the thermal bath, the cooperativity or the single photon cooperativity in the interaction between the light and the mechanics. And these figures of merit, by and large, set what kinds of physics one can access. And if what one is interested in is some kind of strong nonlinearity to get at the full structure of quantum mechanics, within the optomechanical Hamiltonian itself, the only way really to do this is to achieve the single quantum strong coupling that's very well known and accessed in atom cavity QED type of experiments, but which to date, as far as I know, has not been achieved in optomechanical systems. And this would be the regime in which the single photon optomechanical coupling rate is bigger than the mechanical frequency or the optical damping rates. This would provide direct access to the full interesting structure of the quantum mechanics of the system, but so far this is just too hard. The reason it's important, I've tried to briefly illustrate here, again for this audience, this might be a little bit pedagogical, but I'll just go through it quickly. The point being that even if you have a system like a harmonic oscillator and you have prepared it in a perfectly pure quantum mechanical state, like its ground state, if you ask operationally, what experimental signatures can I detect that would reveal some interesting aspect of quantum mechanics? It turns out that states like this are not generically good ways of exploring the rich, interesting structure of quantum mechanics. And just to make that concrete, suppose that I can prepare a harmonic oscillator in its ground state, and suppose I have a perfectly strong projective position detector. So I prepare it in its ground state, I measure position. I re-prepare it in the ground state, I measure position again. I do that over and over again, and I will get a distribution of results that mirrors what we would call the real space ground state wave function. It would look like this histogram. Suppose I do the same thing, but now I have a good momentum measurement, and I measure momentum every time I re-prepare the state. I get a similar Gaussian. And indeed, for any linear combination of x and p, I'll get a distribution that looks like this. And the reason that that is maybe not as interesting as we would like is I can claim that there is a joint quasi-probability distribution over x and p that gives me the a priori probability that this system had a certain position and a certain momentum before I measured it, which is just to say that I can make this probability distribution function in phase space whose marginals are the experimental results. And at that point, there's no obvious distinction between what I measure here and the kinds of predictions you would get from just classical statistical mechanics. just at a temperature such that the thermal occupation width was this big. To contrast that, there are other states, very simple ones as far as the textbook are concerned, like just the first excited state of the harmonic oscillator, in which if I tell this exact same story again, prepare this state, measure position, prepare this state, measure position, build up a histogram, do the same thing with momentum or any linear combination of x and p, I get perfectly reasonable looking data. But if I ask what is the a priori probability distribution in phase space whose marginals would reproduce these results, it's a perfectly well-defined function. Here it is. The problem is that it takes on negative values, and so it is not a probability. So it cannot be interpreted as the system having some pre-existing simultaneous values of x and p, which fluctuate randomly and which I just happen to measure. So if you like, this is a much more direct manifestation of the non-commutation of position and momentum, the impossibility of having simultaneous well-defined values of x and p. So states like this sort of rule out a certain class of hidden variables explanation. If you imagine this as a sort of hierarchy of how much of the structure of quantum mechanics one can access, another big step in this hierarchy, and to be sure, this is a qualitative description of the hierarchy at best. Another big step, though, is when begin to see similar results like the non-existence of an a priori probability distribution over physically distinct objects, well-separated, space-like separated objects. And this is the essential argument behind Bell's original paper. So all of this is to say that the kinds of quantum effects one can access depends very much on what kinds of states one can prepare. At the same time, it's just as important to be able to say what kind of measurements you have access to. I told this story up here pretending that I had this magic position detector that just makes an infinitely strong projective measurement of position, which is a nice way to learn quantum mechanics in the textbook, but we don't really have in the lab. Some generations of optomechanical systems infer the position of a mechanical oscillator by bouncing a bright coherent state of light off the oscillator and collecting that light on a photodiode using some kind of homodyne or heterodyne detection. And in general, even with access to states like Fock states, such measurements tend to obscure structure like this. In contrast, and this is sort of what I'll be talking about today, there are approaches in which one bounces even a bright mode of the electromagnetic field off the harmonic oscillator, but instead of collecting the mean photon number in a photocurrent over here, counts the arrival of individual photons using a photon counter. And this is an important step towards being able to access structure like this in the experiments. So that's sort of what I'm going to focus on working towards in this talk. I should say, so here I tried to give just a pedagogical introduction to what one is really saying when one says more quantum effect or less quantum effect, to what's kind of important about the kind of measurement one does. In this kind of language, it would be just as helpful to have a working operational definition of macroscopicness. Again, there are ways of doing this. They tend to be context dependent, but nevertheless, for now, I'm just going to appeal to your intuitive sense that if it looks big, it sort of is big in at least possibly some interesting kind of way. So the way that we implement this, okay, well, actually, I should maybe pause here. That's the introductory material and background. And I could say I'm happy to take a question or two here before we move on to the kind of the specifics of optomechanics and our devices and measurement scheme.
I don't think we have any questions for now, Jack.
Okay, that's fine. So the way this photon counting story works in optomechanics is the following. If I have an optical cavity and I send in a green laser, every photon that comes out, of course, is still green. If what I have really, though, is an optomechanical system where, say, one of the end mirrors is free to oscillate, then when light comes in, it can acquire phase modulation sidebands from this motion classically. But if what I have here is a photon counting detector that really goes click, each time it goes click, the photon that made it go click was either blue, green, or red. And if a blue photon came out of this system, it must have done so by absorbing some energy from this harmonic oscillator. And so a click from a blue sideband photon corresponds to lowering exactly one phonon out of this mechanical oscillator. whereas a red click corresponds to adding exactly one phonon to this mechanical oscillator. So these clicks carry information about the quantum state of this mechanical oscillator. The problem is that given the weakness of the optomechanical interaction, all but a few photons in a billion are these boring, unshifted photons that provide no information. And since the detector itself doesn't really discriminate in a useful way between blue, green, and red, most of these clicks are, you have no idea what kind of photon they're associated with, whether it's a raising event or a lowering event or a neutral event. So the basic idea here is just to use a very good filter to block the light one is not interested in, and to ensure that anytime there's a click at this photodetector, it really does correspond to an event in which exactly one phonon was added to the mechanical oscillator. And this idea has been around in quantum optics and optical cavity QED. It's been extended to optomechanical systems and employed very successfully in some of these groups here. The specific devices that we use are built with the help of Jacob Reichel's group in Paris. At some level, they're just Fabry-Perot optical cavities, but the way they're realized is really beautiful and extremely helpful. So the Reichel group has developed this wonderful technology for taking single mode optical fibers, laser machining a concavity into their surface, which turns out to be super polished for all practical purposes. You can send it to a coating company. They deposit a high finesse mirror on the fiber. And from our point of view, the beautiful thing is you can take two of these fibers and point them at each other, and you get a stable optical cavity that's maybe hundreds of microns long, tens of microns in diameter. And the really wonderful thing is that this cavity mode is quite well coupled to the light in the fiber's traveling wave. So we have some nice techniques for kinematically aligning these fibers, making them really robust, and epoxying them in place. And once that's done, you have a high finesse optical cavity, 100,000 finesse optical cavity that is completely plug and play. You just run those fibers out of the cryostat. There's no input optics, there's no in situ alignments, there's no mechanical anything. It's literally just a chip, two fibers coming off of it, and on that chip is a high finesse cavity. As such, it's just an empty cavity. So in order to have some mechanical degrees of freedom, what we do is we fill it with superfluid helium. And superfluid helium, I have to say, I think is an incredibly promising material for a lot of quantum optics and quantum acoustics application. As a material, it has this enormous band gap, but much more importantly, it has strictly zero atomic impurities or defects of any kind. Every other element just freezes to the walls. It's a superfluid, so it can't have structural defects or cracks. Electrons and charges don't want to live in there. It's really atomically pure in the same way that like a BEC is, but it has the density of condensed matter. And that means that there's no optical absorption, there's very low mechanical loss. It turns out to have very good thermal conductivity at low temperatures, so it actually stays cold. When we build these devices, the cavities, as I mentioned, are just epoxied in place and are aligned. And the mechanical degree of freedom that we're going to use are the sound waves in the liquid helium, just the garden variety density waves that we would call sound. In the field, this is what's known as first sound, but it's just sound waves. And those sound waves are confined by these exact same mirrors as the light. Glass is a pretty good reflector for sound. And so what you have is a family of optical standing waves in this cavity and the exact same family of standing acoustic waves. And so that means that you now have alignment of the optical cavity with the input light, and the optical cavity is just naturally self-aligned with the acoustic mode, because their acoustic modes and optical modes are defined by the exact same surfaces. So there's no in situ translation stages. I mean, we love AttoCubes, we love JPE, they make amazing products, but it's nice to build something that doesn't require them. Anyway, there are a lot of other interesting things you can do with superfluid helium, but in the interest of time, I'll keep pushing on. So as I said, what we're interested in is the coupling between the light which I've shown one particular mode of in red, and the sound waves in the helium. And so in blue here, I've animated a density wave. This is just an organ pipe wave, a standing wave of sound confined by the glass in the liquid helium. And the way that this optical mode couples with this acoustic mode is the following. It's just that when the sound wave modulates the density, it modulates the index of refraction of helium. There's nothing fancier than that. A more dense bit of helium has a higher index of refraction. That changes the optical length of this cavity. The physical length doesn't change, but as the helium gets compressed and less compressed, the effective length of the cavity is oscillating. And so at the Hamiltonian level, that's exactly the same as a moving end mirror. So that's the notion of coupling. If you like, the analog of radiation pressure on the end mirror is played by the electrostrictive optical dipole force, where this an antinode of intensity tends to draw liquid helium, tends to compress the helium. So that's the nature of the coupling. And one really elegant thing that emerges, which I think is of particular interest to optomechanics community, is that even though this cavity is full of acoustic modes, just like every mechanical device that we make, every cantilever or membrane or phononic crystal has millions of acoustic modes, and we usually kind of want to focus on one. But in principle, all of them detune the cavity. This is a system in which this optical mode is detuned by one and only one of that huge family of acoustic modes. And the reason for that has to do with the simple geometry of this setup. So down here, what I've shown is one optical mode, shown in red here, and I've shown its overlap with a whole bunch of different acoustic modes. So this is the lowest frequency acoustic mode, the next lowest, and so on and so forth. And you can see that if I do the overlap integral of optical intensity in red with helium density in blue, that overlap integral is obviously zero just by the orthogonality of the eigenmodes of this cavity for every mode except for one. So this is sort of the thing that's happening here, is that our acoustic mode and our optical mode have the exact same boundary conditions and the exact same wave equation. So their eigenmodes obey the usual orthogonality relationship. So this is very elegant. This means that you don't have kind of the forest of annoying modes that we try to ignore using frequency discrimination and the like. It's just built into the system that if you see a sideband photon, it had to have been from this mode. This makes life a little bit easier. The other thing, again, that's easier is that because there's no in situ alignment, we just build a whole bunch of these devices. They just go in a little can. The little can only has one fill line for the helium and then one optical fiber for each device. There's no electrical connections, there's no coax, there's no wires, there's no piezos. That's all there is. And so if we wanted to, we could certainly put hundreds, maybe thousands of these in a conventional dilution refrigerator. And at the end of my talk, I will discuss how I think we can take these devices and, with a little bit of extra work, make them really indistinguishable from the quantum communications point of view. But that's for longer term. For present, what we have is a setup that looks very simplified fashion, looks more or less like this. Inside the dilution refrigerator is this device I've been telling you about with an optical mode and an acoustic mode. We have a couple lasers that we use either to drive the device on a sideband, either detuned to the red or to the blue. That light comes into the fridge, comes back out on a circulator. Then it passes through some cascaded filter cavities that are intended to pass only one motional sideband. And those sidebands go to SNSPDs, superconducting nanowire single photon detectors. So the idea is that when you tune the laser, say, to the blue side of the cavity, and then monitor these SPDs, you will see occasional clicks. And each one of those clicks ideally represents the addition or subtraction of exactly one phonon from the system. And so raw data looks like this. We have a cycle where we spend 100 milliseconds sort of getting all these cavities locked up. And then for 100 milliseconds, the cavities are just free running. They drift a little bit, but not too much. And we count the photons that arrive at the single photon detector. And you get occasional clicks. When you zoom in, though, these clicks have extremely high signal-to-noise ratio and extremely good timing resolution. So we know the time of arrival of every sideband photon to better than a nanosecond. Just to give you some characterization of the device, as we sweep the frequency of this drive laser, we see certainly a background. That's sort of this flat contribution. We see a broad peak that's sort of always there. That is one of the Brillouin scattering modes of optical fibers. These are sort of well-known acoustic modes that just live in all single mode fibers. But this peak at 315 megahertz is the sideband photons that are produced when the drive laser is exactly 315 megahertz detuned from the filter cavities. 315 megahertz, I should have mentioned way back here, is exactly the frequency of the one mode that our 1550 nanometer light couples to. So 1550 nanometer light couples to sound waves with exactly half that wavelength, and a helium sound wave with 775 nanometer wavelength has frequency 315 megahertz. So we expect all our sideband photons to be here. This line shape is just the line shape of these two filter cavities. That's what the fit is to. So as we sweep this drive laser, the sideband photons are kind of always being emitted, but it's only when they are resonant with the filter cavity that they actually get through to the photodiode. So that's what this line shape is here. So as I mentioned, we have some background counts. We have the fiber Brillouin scattering, but then everything that's left over is the blue optomechanical sideband. We can do the same thing just by putting the laser over here on this side, in which case the data looks very similar, same kinds of backgrounds, the sideband peak, and this difference between them is an effect that's known as the quantum sideband asymmetry. In everything that I talk about from here on out, we'll kind of always be working with photons, with these photons. And this background we've verified has nice Poisson statistics. And so as appropriate, we'll be subtracting that out in what I talk about. First, though, in order to maybe convince you that we understand what these phonon sidebands are, this is just the height of those peaks, this red peak and this blue peak, as we change the temperature of the dilution refrigerator. And you can see a couple things here. One is that they both scale with the temperature of the fridge, as one would expect with the thermally occupied acoustic mode. They look like they stay in equilibrium with the fridge temperature down to 30 millikelvin or so, give or take. And there's this persistent difference between the height of the red and the height of the blue, which is what gives us, among other things, confidence in assigning this to the quantum sideband asymmetry. It also gives us a natural way of calibrating these count rates. We can characterize the device a bit further by keeping the fridge temperature cold, but cranking up the power in this drive tone. And so when the power is very low, we just see a difference between the red and blue sideband. As we increase the power, two things happen. Both the blue counts and the red counts go up. This is just because the device is getting hotter. We shine more laser light on it. It does warm up a little bit. The blue counts go up much faster than the red counts, but this is just a consequence of the fact that the blue data is taken by putting a laser on the blue side of the cavity, which tends to anti-damp the motion, whereas the red data is taken with the laser on the red side, which tends to damp the motion. So what's shown here is a fit in which this trend here is the heating that you would get from a very simple model of thermal transport from hot spots on the mirror out through the liquid helium. This gap here is the quantum sideband asymmetry, and then the difference between red and blue is just the well-known optical spring dynamical back action effect. And so the fit parameters here are sort of thermal conductivity coefficients and the optomechanical coupling rate, and I think that's about it. So all this is to say is that the device is understood pretty well. It's also worth saying that all of this phenomena is just gotten from the mean phonon rate. And so in principle, this is all data you could take with homodyne or heterodyne detection. But the fact that we're using photon counters means that there's a lot more information buried in the data, which is to say the photon's individual arrival times. So that's what I'm going to talk about next. So as I mentioned, each click in the detector is really a sort of nanosecond timestamp for the arrival of that sideband photon. And so a natural way to characterize the statistics of these arrival is just through their two-point correlation function, what's known as G2. So we have a long string of photon arrival times. We calculate their G2. And when we drive the optomechanical device on the red side, it looks like this. It starts at 2, decays to 1 with a single exponential, as shown by this fit, and also shown in this logarithmic plot. That's what one expects for an acoustic mode that is in a thermal state. And it's particularly nice that the fact that this is a single exponential is a consequence of the fact that the optomechanics really only measures a single acoustic mode. This is really nice single mode acoustics. If we want to interpret the photon G2, though, in terms of a phonon G2, there are some subtleties. When the device is driven on the red side, the linearized optomechanical Hamiltonian maps the photon creation and annihilation operators directly onto the phonon creation and annihilation operators. So the photon G2 really is the phonon G2 when it's driven on the red side. But when the device is driven on the blue side, the optomechanical Hamiltonian gives you a two-mode squeezing Hamiltonian. And so the photon G2 is really the the G2 of phonons that you would calculate using anti-normal ordering. So we call this the H2. So anyway, that's a distinction to keep in mind. But if what you have is an acoustic mode in a thermal state, there's no operational difference in terms of what you see. It's still a single exponential from 2 down to 1. Looks the same in both cases. I should say the apparent difference here is just the fact that when the laser is detuned to the red, there's some anti-damping, and so the coherence time of the mechanical oscillator is short, as opposed to when it's blue. Sorry, in the blue case, it's anti-damped, and in that case, it's just stretched out, but it's the exact same physics in both cases. With all of this data, we don't have to stop at the two-point correlation function. We can also look at all triples of counts, and each triple of counts gives you 2 times. And we can say, hey, given that I got a click here, what's the chance of getting 1 click a certain time later? That's this axis. And a third click another time later. That's this axis here. So this is what's known as G3. And this is the data here for data on the red side, on the blue side. Again, interpreting this in terms of phonon correlations. The red data is the normally ordered correlation. The blue data is the anti-normally ordered. In both cases, you can calculate what the prediction would be for a thermal state, and that fit is shown here as the sheet. It's a little hard to see in 3 dimensions, so I've also just shown the residual to give you a sense of the quality of the fit. We don't have to stop there. We can go to 4-point correlation, so we can take 4 lets of data, and every one of them gives us 3 times. At this point now, the data is a 3-dimensional data cube. There are, for every quadruple of counts, there are 3 timestamps. So we do take the entire data cube. We do fit the entire data cube, but just for simplicity, I'll just show you one slice of that data cube here, again, with a fit to what's expected for the thermal state. And if the fit parameter that we take here is the time constant of the decay, and then the coefficient that sets the value of this correlation function at 0 delay. And for the 2-point correlation function, that's supposed to be 2. For the 3-point correlation function, it's supposed to be 6. For the 4-point correlation function, it's supposed to be 24. And that's all reproduced pretty nicely by the fits. So I'll say a little bit more about this. Actually, I'll just say it now. So all of this is to say that the acoustic mode shows the statistics one would expect for a thermal state. So in some sense, there's nothing exciting or exotic or quantum mechanical about this data. But it is, I would just say that it's kind of nice that we now don't have to assume that the acoustic mode is in a thermal state. If you measure the mean number of phonons and maybe even the variance, that's nice, but if you want to say that it's actually in a thermal state, you have to measure the higher accumulants of those distributions to really pin it down. And so if you like, this is a characterization of the Gaussianity of the state out to the fourth cumulant. So if you like, we verified that it really is thermal. We can also push a little further into this data and do post selection on this giant data set. For example, if you have just gotten one click, the chance of, if you've just gotten one click, the mean intensity of sideband photons is doubled. That's what this is shown here. Or if you get 2 or 3 clicks, if you've just gotten 3 clicks, the chance of getting a fourth one is quadrupled. We can also say, look, let's calculate a G2, but only for data in which we just got a click. So this is the G2 of sideband photons, where it's not over the entire data set, but it says, look, we just got a click in the last microsecond or so. Then what, if we throw away all other data and only keep that data, what does the G2 look like there? And again, it shows what you'd calculate for these conditional probabilities for a thermal state. Again, all of which is just to say this is a very thorough characterization that it's really single mode optomechanics of an acoustic state. So this is a starting point, and we want to start to move beyond this and get into some, instead of thoroughly characterizing maybe boring physics, starting to look at some more interesting stuff. And I can tell you some first steps there. So one first step towards that is to not just take the mode that we get by letting the acoustic mode equilibrate with the thermal bath, but actually apply a drive to it. And the way that we do that is we send 2 lasers into the cavity. They come from the same laser, but one tone gets a frequency shift and then they're recombined. And these are the 2 drive lasers. Their frequency is chosen such that the beat note they make in the cavity can be varied in frequency and basically swept over the resonance of the acoustic mode. This is just a nice way to apply a linear drive to the acoustic mode. And then we're going to measure what happens by having a detection laser that's detuned to one of the sidebands, with the point being that when the acoustic mode starts to shake and put sideband photons in things, it's only this mode whose sideband photons pass through the filter cavity and get detected. That's the basic setup, and the kind of data that we take looks like this, where we're sweeping the frequency of the drive, sweeping the frequency of the beat note. And here what we're counting is the rate of clicks, the rate of sideband photon arrivals at these detectors. And we do that for various strengths of these driving tones. And you can see qualitatively that it looks pretty nice and linear. If we just fit these to Lorentzians and calculate sort of the height of the signal that we're getting, and then calibrate that in terms of the mean phonon number that's being excited inside the acoustic mode, this drive looks nice and linear all the way up to something like 20 or 30,000 phonons. And there's no sign that we're hitting any kind of nonlinearity. That's just as much power as we can get out of these devices at present. So all this is to say that it looks like the acoustic mode and all of its interactions are nice and linear all the way up to a driven phonon number of about 40,000. But what we would like to know, if we want to make some use of this, what might be now a coherent state, right? We start very close to the ground state, 1 phonon or so. And we would like to, the goal of this is to make a high amplitude coherent state. And this looks like everything is nice and linear, but it would be nice to know whether that highly displaced state retains its original purity. There are a lot of, the optimist would say, well, of course it does, but just in practice, there are a lot of reasons why it might not. So if there's phase noise on these lasers, or if there's parameter noise in the resonant frequency of this mode, that will take this big drive and sort of make the driven state wander around in a way that would result in reduced purity. So in order to characterize the purity of the driven state, what we do is we take those sideband photons and look at their G2, look at their correlation. And what I showed you before was this light pink data where no drive is applied to the system, and it just looks like what you'd expect from a thermal state. It has a G2 that goes to 2 and relaxes to 1. As we start to drive the system harder and harder, it changes qualitatively and definitely approaches what you would expect kind of for a coherent state, which is just a G2 that's just 1, a constant of 1. We can be more quantitative, though, and look at this data more carefully. So this is not the exact same data set, but similar data where what I'm plotting is G2 minus 1 on a logarithmic scale. And what you can see is that when the drive is very low, it goes from a G2 of 2, decaying exponentially. And as we drive it harder and harder and harder and harder, it goes closer and closer to a coherent state, but it still retains a little bit of its thermal character. And what we'd like to know is that thermal character, is this noise blob getting bigger as we drive it because of some technical problem or not? And as far as we can tell, the answer is no. So this shows the G2 of 0, just acquired by fitting data like this and extrapolating back to 0 as we drive it harder and harder. And this axis, I should say, is basically the mean phonon number. So as when the mean phonon number is much less than 1, when it's basically just in its thermal state, it looks like a thermal state. And as you drive it harder and harder, it looks more and more like a highly displaced thermal state, almost a coherent state. This is that same data, but just plotted on a log scale with this 1 subtracted off, so that you can see that it really does look like it's retaining its purity out to high phonon numbers. So that's everything that I wanted to say about the experiments that we've done so far. Just as an amusing point, this is equivalent to saying that the noise temperature of this mode stays what it is at base temperature, 20 or 30 millikelvin, even when it is displaced by an amount that would correspond to room temperature. That's what 30,000 of these phonons would be. So maybe I could pause here and take questions about the experiment before talking about just maybe spending 5 minutes or so on future directions.
Yeah, so we have a question from a YouTube video from Fabio Pistolesi. Just send you in the chat, yeah. And the first slide discusses the coupling of light due to the oscillator. Can you explain better what do you mean by unitary coupling, please?
Oh, just something that preserves, something that doesn't involve dissipation. So like a photothermal interaction would represent a coupling between the number of photons in the cavity and the force on the end mirror, but it wouldn't preserve quantum states. So that's all I mean.
Okay.
Whereas radiation pressure does preserve the purity of the joint system's quantum state.
Jack, I have a very technical question, but so you use 2 filter cavities in series?
Yes.
I guess it's because one is not enough, but what's the finesse of this filter cavity? What are the numbers you need to reach?
Yeah, so they have line widths of 1 megahertz, and they have a free spectral range of either 1 gigahertz or 10 gigahertz. So finesse is like 1,000 or 10,000. And if there's no sort of magic there, we have this very bright laser that's detuned by 315 megahertz. And if you're going to put a filter cavity to try and catch the sideband photons, your filter cavity has a peak there, but unfortunately it still is accepting some of the photons from your drive. It's detuned by 30 line widths or something, but you only expect about, for every 100 million of these photons, you only get about 1 photon over here. So you need your filter cavity's Lorentzian to be suppressing by at least 90 dB, 10 to the 9, at this frequency shift over here. And you could either do that with 1 very narrow cavity, but for various technical reasons, it seemed like it was going to work better for us to do it with 2 cascaded non-heroic cavities.
And are you sensitive to losses? I mean, well, that's one reason sometimes not to go to much higher finesse.
Yes.
Because you want a good ratio between your transmission and your losses.
Yeah. So just to be clear, these filter cavities are commercial fiber cavities from Micron Optics in the US, and when they're cascaded, they have 4% transmission. So each one is 20% transmission. So we're definitely doing all of this at pretty low overall efficiency. All of the measurements that I've described to you don't really suffer from that very much. I mean, you have to sort of take data for longer, but there's no like if we're really trying to look at Wigner function negativity or something like that, this loss would hurt us. But for these kinds of statistics, that loss isn't bad. We're in the process of building, that was just our first attempt. We're in the process of building some homemade filter cavities that are intended to have much higher throughput. But for now, we're just using the commercial ones, and it's okay.
Because I think you did some homemade filter cavities maybe 10 years ago. Or...
That was to suppress noise on the drive laser for a different experiment. But yeah, it's the same basic kind of thing.
Okay, no more questions, so you can continue.
Okay, so in the last couple minutes, I'll just tell you about two future directions that we're working on. So one is that one thing that I didn't really advertise is that these devices have rather low mechanical quality factor, which is disappointing because liquid helium really is kind of perfect as an acoustic material. But the fact is that in our devices, the only thing that confines sound waves to the helium is the acoustic impedance mismatch with the glass. So that means that every 100 round trips or so, a phonon just travels out into the glass. So we would like to improve that for a number of reasons. And two ways of doing that is that we have in our lab now mirrors in which there is a dual band DVR coating, a series of layers that are high finesse for the optics, but then a second series of layers that are high finesse for the acoustic mode. And this involves some technical surprises that I could go into if you're interested, but it's basically just a dual band DVR. And our hope is that these acoustic coatings will give us an optical quality factor that's 100 times bigger than what we've got to date. In addition, the cavity can be longer, so the phonon storage time should approach a second. That's the hope of these devices. We're also working with Jacob's group to realize fiber cavities that form a triangle cavity to take advantage of this incredible fact that the speed of sound in liquid helium is very low. So it's very easy for phonons to undergo total internal reflection in helium. In fact, the Fabry-Perot cavity is the only geometry really in which you don't get that. So all that's to say is that if you build a ring cavity, you have to put on optical layers to confine light to the ring cavity, but these sound waves will just be confined by total internal reflection naturally. And at that point, the finesse, the acoustic finesse is infinity or something like it. In practice, it's limited by things like surface roughness, which we know how to estimate. And again, we think we'd get another 3 orders of magnitude in the acoustic mode quality factor. Both of these approaches would result in phonon storage lifetimes approaching 1 second, which would be exciting for a lot of applications. At present, we get sideband counts about every 10 milliseconds, and a phonon state that's produced by that only lasts for about 0.1 milliseconds. So there's no hope of kind of closing the loop in a quantum control way with the present devices. But if you're getting sideband photon counts every 10 milliseconds and the resulting acoustic state lasts for a second, there's some very interesting quantum control that one could implement. The other thing that we want to take advantage of is this really elegant, simple geometry of the optical and acoustic mode and do the following. If we make several devices in our fridge already, we enjoy not having any piezos, but if you're willing to add 1 piezo per device, such that you can tune each cavity to be resonant with a single laser, this is not extremely difficult to do, then you send in a laser that is driving all of these cavities through the appropriate circulator. And this is obviously a really cartoonish picture, and then the light comes out and you get a click on the single photo detector. You know that you added exactly 1 phonon to this system, but you don't know which device actually acquired it. This heralds the production of a phononic W state, which has a lot of use for quantum information protocols. And it's important to realize that this is being done in an optical fiber device at 1550 nanometers. So these nodes wouldn't even have to be in the same dilution refrigerator. They could be separated by kilometers of fibers, and each one of them would have a corresponding memory based on this technology on the order of a second. So once you generate that, you have sort of a secondish time scale to implement quantum communications protocols. This is kind of the basic DLCZ approach that we would like to exploit. So this is another thing that we're working towards in our lab. But it's really all based on kind of existing technology and hopefully just one incremental generation of added effort. So that's the end of my talk. Just as a quick summary, what I told you about are these superfluid filled cavities that give you some very nice single mode coupling, keep things cold, and combined with single photon detectors, allow one to measure things like higher order phonon statistics in the acoustic mode. And we've shown specifically that we get relatively pure states that look as they should for a thermal system, and that we can drive them up to a coherent state, or if you prefer, a displaced thermal state with mean phonon number in the tens of thousands. And we think these devices are promising for pushing into a variety of applications, some of which I just told you about. I should mention that we have openings for postdocs. We have a couple other projects going on in our lab. This is the one that I just told you about. We're also interested in the optomechanics of pure superfluid devices. So we've learned how to magnetically levitate millimeter scale drops of superfluid in vacuum. And we hope to confine light in their optical whispering gallery modes and access some really new regimes of quantum optomechanics. We also have a project in studying non-Hermitian dynamics in coupled oscillator systems. Turns out optomechanics are nice for doing that. And specifically, we've been exploring what happens when you have three modes that have a full non-Hermitian degeneracy. And what we've been able to measure is that around that triple non-Hermitian degeneracy, the family of double degeneracies constitutes a trefoil knot in parameter space, and that closed loop operations around that trefoil knot accomplish braiding operations over the individual eigenmodes. So that's everything. Let me again just thank the students, and especially Yogesh and our collaborator Jacob and our theory collaborators, and thank you very much for your attention.
Okay, thank you, Jack. Well, when we started the seminar series, we wanted a very good talk to start, and this is what we got. So thank you.
Okay, thank you.
Thank you. So about the DLCZ device that you mentioned, I was wondering, so how similar can the cavities be? Because okay, so they're locked to the same wavelength, but that means that they have the same length, plus or minus a few half wavelengths. But is that a problem for?
Yes, you're asking the right question. This is the super cartoony story. For real indistinguishability, you don't, if you lock them all to the same laser, they're all offset by some integer number of half wavelengths. But the frequency, but the locking is very good. You still have to worry about the temporal mode of the sideband photon that comes out. So they all need to have reasonably similar line widths. If they have different optomechanical coupling rates, if you get a click, it probably came from the one with the really big optomechanical coupling rate. So you need those to be similar. You need the polarizations to be similar. You need the spatial modes to be similar. A lot of that, I haven't gone through all the numbers in that, but these devices look promising for all of those things. When we make these things and we coat them, we get pretty reliable finesse, pretty reliable line widths. The optomechanical coupling rate is just set by the volume of these guys. Like if you just calculate in MATLAB or COMSOL the overlap integral of the full 3D Gaussian optical mode with the acoustic mode, comes out very close to that. So it's very predictable. So we think that temporal indistinguishability will be pretty good. The optomechanical coupling rate indistinguishability will be pretty good. All the transverse mode stuff is handled by the optical fibers. So you're asking the right questions, but I'm optimistic. I don't know that it'll work, but it seems worth pursuing.
And how many cavities do you have in mind?
We'll probably start with 2, but as I said, like each device, has a footprint of a few square millimeters, a few cubic millimeters, and you need to bring in one optical fiber for each one, and in this case, one DC line for the piezo. I don't think it would not be hard to make 100 of these. And it would certainly fit in a standard dilution refrigerator with no giant effort.
Okay.
But we'll probably start with 2 and work our way up.
Yes. Question
yeah.
from...
Yeah, a question from YouTube. So you speak about radiation pressure and later on dynamical back action. So what is the difference in terms of cooling and amplification?
So this device, if I understand your question, this device is just a totally standard optomechanical Hamiltonian. If you put the laser on the blue side, it anti-damps. If you put it on the red side, it damps and cools. But maybe one thing that's particular is that the acoustic quality factor is rather low. So there's kind of already a lot of mechanical damping. And so we don't do any laser cooling. In fact, yeah, that data that I showed, one takeaway from this is that you put on a red detuned laser and you crank up the power and the device actually gets kind of hotter. So that is reflecting the fact that the little bit of real physical heating from optical absorption just about cancels the little bit of optical damping in our devices. So so we don't do any laser cooling because we can't. The acoustic quality factor is too low. So that is something that we also hope to take advantage of in these devices here that have line widths that are maybe 4 orders of magnitude lower between the higher reflection and the longer cavity. This would finally allow us to do some laser cooling. And so if the fridge can get us down to about 1 phonon, hopefully in these devices we could laser cool down to a little bit less than that.
Okay. Another question from Fabio. He said, is it possible to generate and detect squeeze mechanical states with the same method?
Yeah, this is not something I know a ton about, but I think the same basic protocols of driving simultaneously on the red and blue sideband and getting clicks works. And so this theory and the experiments are well carried out in CW kind of approaches with heterodyne and homodyne measurements. I think essentially the same things play out with photon counting detection.
Okay. No more questions. Many thanks from many people.
Yeah.
Thank you. Thank you very much. It's a pleasure to chat.
Okay, so I guess we're good. So thanks again, Jack, and thanks everyone for